Okay, what factors will affect the resistance of a conductor? Length, thickness, and temperature, as well as the nature of the conductor. So I like this little picture. In a short conductor, look, the electrons go, so soon, we made it. But then in a long conductor, they're like, are we there yet? Must go on. So it's really hard work for electrons to get to the end of a long conductor. So the resistance increases with the length of the conductor. There's also the thickness of the pipe. If you are an electron and you're trying to get through a really thin conductor, squeeze, scooch, you can't really get through. So thin wires have high resistance and thicker wires have a lower resistance. So that's why, like if you look for instance in your car, the battery cables taking the current directly out the battery are huge to decrease the resistance so that the current can get to the starter of your car. And also in the power lines up in the sky, you can't see them, but they're very fat cables because it decreases the resistance. So a fat cable has, or you can say instead of fat, one with a large surface area. A large surface area has a decreased resistance. And then with temperature, the increase in temperature increases resistance because the poor little electrons have to navigate around very excited atoms which are bouncing up and down a lot, and they bump into stuff and resistance increases. Okay, so here it is in words instead of in a cute picture. The longer the conductor, the greater the resistance. The greater the diameter of a conductor, the less the resistance, because it's really easy for the electrons to pass through a fat pipe. Okay. The temperature of the conductor, the higher the temperature, the greater the resistance. So this goes back to when we study metallic bonding in chemistry. If you've got a metallic core, remember temperature is a measure of the average kinetic energy of the particles. So average kinetic energy, high temperature, high kinetic energy means that if you are hot, you are going to vibrate more. And when the electrons try and pass the metallic cores, they bump into them more frequently. So the rate at which they are moving decreases, and then the current decreases, and so it's got a greater resistance. Okay, now this is actually the part I want to look at. How do we answer questions with this? This is the most common layout of a question. These two circuits are the same. They just put this resistor around a corner. But if you are a little electron going out the battery, which I strongly encourage, if this circuit is complete and you're an electron leaving the battery, you come out here, you go around the corner, you pass through resistor 3, you get to here, you've got a choice, do I go resistor 1, resistor 2? But either way, you can come home and get back to the battery when the switch is closed. This is exactly the same here. Little electron comes out the battery, goes through resistor 3, can choose resistor 1 or 2, and gets back home. So when you look at this and you look at this, it's kind of like what's going on here. And the only way to figure it out is to pretend to be an electron and go all the way home. Okay, so you have to follow the path of the current with your finger, with a pen, with another diagram somehow. How do we work on these questions? They usually are going to do something, make you do a calculation based on the resistances. So what we have here is we have a series resistance and a parallel resistance. Okay, so what you can do is you can convert these two resistors into an equivalent one resistor, the equivalent or the effective resistance. Each two resistors have their own resistance, but we can't use the series circuit formula unless this was one resistance. So what we do is we take these two parallel resistors, we do some maths using the parallel resistance formula, and we get a number. These two resistors together will have one effective resistance. And then once we've calculated this one effective resistance, we can look at this as a series circuit with R3 in series with the parallel resistance. So you can see I wrote it here. The total resistance is going to be the parallel resistance plus the series resistance. So when you do a calculation, you first work out the parallel resistance, Rp, okay? And you can use the quick and dirty formula, or you can use the proper 1 over RT equals 1 over R1 plus 1 over R2 plus ... Okay? So then the moment you've worked out Rp, if you want to get the total resistance, you add the parallel resistance to the series resistance, which in this case is called R3. and that'll give you the total resistance, and then you can do V equals IR on the whole circuit because the current is the same everywhere, and they've usually given you the voltage out the battery, and then you've effectively turned all three of these resistors into one number, which is the total resistance for the whole circuit. So that's the main way you go do this. Convert the parallel to one number, and then you add the parallel one number to the series, and then you've got a single number for the whole circuit. Okay, so it works out RP is one resistor, RS is another resistor. Okay, this is the other thing that often comes up in questions that you have to pay attention to. If you're going to remove a parallel resistor, the resistance is going to increase. So now remember here, two resistors in parallel have a lower resistance than either of these two resistors by themselves, okay, because of the way parallel resistors work. So this parallel resistance here has got one value, but if I take one of these resistors out, then I only have a series circuit. So can you imagine that R2 is gone. If an electron comes out here, it goes through R3, and it can only go through R1, and that effectively makes R3 and R1 a series circuit. And the parallel resistance is always smaller than the resistance of the individual resistors. So now you've taken out a resistor, the resistance actually increases when you remove a parallel resistor, so the total resistance of this circuit will increase. So they say things like, what will happen to the total resistance if R2 is removed? So the total resistance is going to increase even though you've taken out a resistor, because the parallel resistance increases when you remove a resistor. Then they say to you, what happens to the resistance if you remove R3? Now R3 is in series, so the current now just has choices. Okay, it doesn't have to go through R3. The total resistance is going to decrease because the series resistance has been removed. It's questions like that that they ask you that you need to pay attention to, because you need to use this knowledge of parallel resistors, that the more resistors you add in parallel, the smaller the total resistance gets. So here, if you have a look at this, when the switch is open, can any electrons get home when the switch is open? Okay, no electrons can get anywhere when the switch is open. So the voltage is the voltage supplied by the batteries, is 24 volts. What's the reading on the ammeter? Here's the ammeter A1, okay, because it says A1. There's no current flowing in the circuit, so look, the electrons can't get home. If the electrons can't get home, there's no current. Now when we close the switch, it says calculate the equivalent resistance of the circuit. So the equivalent resistance is, if instead of having 3 resistors, we only have 1 resistor. So we have to work out what is this parallel resistance as one number, and then add it to the series resistance. So you can see here the total resistance is equal to the series resistance plus the parallel resistance. So the series resistance is easy, it's 8. What is the parallel resistance? You multiply the two numbers, 8 8s are 64, and you divide it by 8 plus 8, which is 16. So you've got 64 over 16, which is 4. For those of you who can't do mental arithmetic, go check me on your calculator. And you get a total resistance for the circuit of 12 ohms. Then it says to you, calculate the reading on voltmeter 2. Where is voltmeter 2? Voltmeter 2 is over here, okay? So you can use V equals IR if you like. If you work out what the current is in the circuit and you know the voltage, you can work out what this will be. But what you can also do is use your knowledge, and this is what you're supposed to do in grade 12. You're not in grade 12, in grade 10. You're not supposed to use V equals IR. You're supposed to say to yourself, a series circuit is a potential divider. Okay, so it's going to divide the potential, it's going to divide the voltage. Remember, potential and voltage, you measure potential in volts. So the volts are going to be divided up between the parallel resistance and the series resistance. And the effective resistance of the parallel resistor, remember we calculated it, it's 4. Okay, remember that always the parallel resistance is less than either of the resistors in the parallel circuit, and this is 8 ohms. So this is 8 ohms, and this has an effective resistance of 4. So we've got 24 volts in the circuit, and it's going to divide in this ratio. Okay, So because a series circuit is a potential divider. So we say in the ratio of 8:4, the total is 12. So 8/12, yeah, remember ratios, 8 plus 4 gives you 12, and this is 8/12 of the total. So 8/12 of 24, 16 volts. So you can do it with V equals IR, but you also need to learn how to do it with the circuit as a potential divider. And then the last thing here is this is what a triple scale ammeter or voltmeter looks like. If it was a voltmeter, it would look exactly like this, but it would say DCV, and these would all be in volts. So when you want to use these in the practicals, positive is red, negative is black, okay? So you always work with the biggest current. So you put one little plug in here, and you start putting the plug in the biggest number. Okay, this is a milliamp. Look on the scale, 5 amps, 50 milliamps, 500 milliamps. So a milliamp is 1,000th of an amp. So 5 amps, and this is 50 thousandths of an amp. So it's a fraction. So you put the thing in here, the black in here, the red in here, and if your little scale doesn't move, then you don't have that much current. So then you put it in the next one, and if it doesn't move, you put it in the last one. But if you've got a big current and you start in the small 50 milliamp slot, you're going to blow up the ammeter, and your teacher's going to get really angry with you, like really angry. So you start in the big one and you move down to the smallest one. And then you check, am I in, the black one stays there. So if you're in the middle connector, then you read off, see this says 500, you read off the 500 milliamp scale. So if you're over here, if this little needle goes over here, then you're on reading off, and you're on the middle one, you read off the milliamp scale. This is 150 milliamps, okay? But if your connector was in the 5 amp box, then this would be 1.5 amps. And if you were in the 50 milliamp box, this would be 15 milliamps. So you have to read the scale on here, depending on what is going on with this. Okay, and that's where this ends.